Hello, we are Flint & Sons, and we are in charge of the SDSU West Campus development, and this is our team.
Hi, my name is Colin Kilborn, and I was in charge of developing the Stormwater Quality Management Plan.
My name is Christian Diaz, and I was in charge of developing the water distribution study.
Hello, my name is Brandon Maddox, and I was a part of the transportation analysis and estimation.
My name's Andrew Coulter, and I was in charge of the sewer system analysis.
My name's Jordan Zimmer, and I was in charge of developing the geotechnical and site civil evaluation. And Kelly Flint was in charge of developing stormwater.
Before any other studies may be completed, a geotechnical and site civil evaluation must be completed in order to determine site stability and proper slopage of the proposed grade. We obtained boring data from the field, which was provided in a geotechnical study conducted by AECOM. Using that data, we were able to determine if the site was safe for development. Factors such as slope stability were seen to be within the acceptable limits, and we determined that liquefaction due to ground motion is the only realistic hazard that must be mitigated. As seen in the figure to the right, several outlying areas were comprised of loose sand and gravel. We concluded that recompaction of the afflicted sandy areas is to occur if development is to occur on top of them in order to avoid liquefaction. After the geotechnical evaluation was completed, we then conducted a site civil evaluation to determine proper grading. We found that the existing stadium will require about 195,000 cubic yards of fill soil, and the proposed stadium will require about 140,000 cubic yards of soil excavation. The overall site grading that occurs afterwards will leave about an excess of 145,000 cubic yards of cut soil. So after all this grading is completed, there will still be an excess of 90,000 cubic yards of soil that will have to be exported from the site. Of course, after all of the grading is completed, recompaction of the soil will have to be completed to ensure proper stability of the soil for future development.
A transportation analysis was conducted in order to maximize efficient and easy vehicle access to the new San Diego State University West Campus development. Through trip generation analysis, we predict an increase in weekday traffic flow from students, faculty, visitors commuting to and from campus. Due to the reduced stadium capacity, we expect to have a decrease in game day traffic impact. A level of service analysis was conducted on the main entry intersection, Friars Road and Mission Village Drive, for existing and future traffic flows. From our analysis, we concluded that a second right turn lane should be added to westbound Friars Road. We recommend that a three-way intersection be added at the northeast of the development and the existing bus access at the southwest side of the property be permanently opened and accessible. Looking at this side-by-side level of service comparison with and without the proposed development recommendations, we can see that the overall level of service of the future conditions of the SDSU West Campus development are better than that of the future level of service without the SDSU San Diego State University West Campus development.
Drainage is an important aspect of the site design due to the project site's proximity to the San Diego River and position within the 100-year floodplain. Because the existing storm drain system lies under proposed structures, the entire existing system will be excavated and a new system will be installed. The proposed drainage system is to be comprised of 6,210 linear feet of reinforced concrete pipe with an inner diameter of 48 inches. To determine the peak flow and select appropriately sized pipes, the proposed site was divided into 4 main drainage basins, each corresponding to one of the 4 drainage outlets in the proposed system, and a total of 29 subbasins. 100-year peak flow calculations for each individual subbasin were done using the rational method. Because total peak flow for each main basin is composed of runoff entering at different times to different parts along the drainage system, the modified rational method was used for junction analysis to compute the overall peak flow from the site. 100-year peak flow from the proposed site was calculated to be 511 cubic feet per second, a reduction of approximately 50 cubic feet per second from the 100-year peak flow under existing site conditions. This is likely due to the average of 20% pervious area that will exist on the proposed site post-construction. Peak flow from the site will be further reduced by proposed best management practices, or BMPs. The proposed drainage system, in conjunction with the increased percentage of pervious area and proposed BMPs, will help limit the amount of runoff discharged into the San Diego River and reduce the likelihood of flooding on the site.
In order to improve stormwater runoff quality and reduce runoff volume, we have proposed multiple BMPs to be implemented throughout the site. These BMPs will be incorporated throughout the site in the appropriate drainage management areas, or DMAs. A map of the DMAs is shown here. BMPs that affect the runoff factor, or C value, include green roofs and impervious area dispersion. Green roofs will be implemented on all appropriate building rooftops throughout the site. Impervious area dispersion will be incorporated in all walkways and open areas throughout the project site. These BMPs will lower the runoff factor, which then leads to a reduction in runoff volume. These BMPs also provide treatment through vegetation. Calculations were performed using the area-weighted runoff factor equation. The equation, calculated runoff factors, and corresponding drainage management areas can be seen here. BMPs that offer a reduced design capture volume include tree wells, cisterns, and rain barrels. These BMPs capture stormwater during rain events, which leads to a decrease in overall runoff volume. Tree wells will be implemented in walkways, sidewalks, and open areas throughout the site. Cisterns will be fitted to all appropriate buildings throughout the site, and rain barrels will be fitted to all faculty housing units. The stormwater capture via rain barrels and cisterns will be reused for toilet flushing and irrigating the surrounding landscape. Calculations for reductions in runoff volume were performed using the design capture volume equation. The equation calculated design capture volume reductions and corresponding drainage management areas can be seen here. The remaining design capture volume will be treated and partially retained through biofiltration with partial retention. The proposed biofiltration with partial retention BMPs include planter boxes and vegetated filter strips. Planter boxes and vegetated filter strips will be dispersed throughout the project site where appropriate. These BMPs offer a reduction of 23,685 cubic feet in design capture volume, which was calculated using a simple sizing worksheet provided by the final model BMP design manual for San Diego region. They also provide stormwater quality improvements through biofiltration.
Existing water utility infrastructure at Qualcomm Stadium is served by a 48-inch steel cylinder rod-wrapped water pipeline labeled Alvarado Second Pipeline. The Alvarado Second Pipeline runs along the northern boundary and bends at the northeast corner along southbound Interstate 15. A 16-inch diameter ductile iron pipe runs from the middle eastern boundary of the site, southwest of the site. A 12-inch diameter asbestos cement pipe runs from the east to west toward the existing stadium before connecting to a network of 10-inch diameter asbestos cement pipes around Qualcomm Stadium. To determine an adequate water supply for the development, the water demand, peak water demand, and fire demands were calculated according to the City of San Diego Water Department Capital Improvements Program Facilities Design Guidelines. 4 of the existing water mains conflict with the location of the proposed stadium, faculty housing, and student housing. New structures cannot be built on top of existing water mains, so it will be necessary to relocate those existing water mains. Water mains need to be installed within the right-of-way or in streets for easy access and repair. To accommodate the proposed layout, it will be necessary to relocate the Alvarado Second Pipeline farther north behind the newly proposed stadium. The conflicting 16-inch ductile iron pipe would need to be reconnected further east out of the way of the proposed faculty and student housing. Both 12-inch and 10-inch asbestos cement pipes that connect and encircle Qualcomm Stadium should be abandoned altogether. To best meet the water demand, 2 new connections are recommended as shown. One connection should begin along the northwest corner of the second Alvarado pipeline, along with a 10-inch pressure-reducing valve at the junction. The other connection should include a 6-inch pressure-reducing valve and begin at the pressure-regulating station along the intersection of the relocated 16-inch pipe and 48-inch pipeline along the eastern boundary of the site. This second connection will be positioned along the building before bending west into the public right-of-way toward the center of the site. At the proposed student housing at the center of the site, a surrounding circular network would link the first and second connections. 2-inch diameter PVC service laterals should be used to send water from the proposed distribution mains to the buildings. All recommended connections, as well as the circular network surrounding the central student housing, should be 12-inch diameter polyvinyl chloride pipes for an approximate total of 7,050 feet of pipe length. The 2-inch PVC laterals are approximately 324.19 feet in length, and there will be 7 hydrants on site. To satisfy the criteria set forth by the City of San Diego's Water Department guidelines, Water modeling software Synergy Water 4.0 was used to successfully meet the following constraint criteria. Every water main in each existing pressure zone is capable of supplying a minimum static pressure of 65 psi with no demand on the system. Operating pressures under the maximum day demand condition in the system from a fire and under peak hour demand conditions fell no more than 25 psi below the static pressure with no demand on the system, and residual water main pressure was at least 40 psi. When analyzing a system with one source of supply out of service, pressures fell more than 25 psi below static pressure but did not exceed more than 40 psi with no demand on the system. All scenarios modeled meet the City of San Diego's criteria during maximum day demand as well.
Existing sewer lines on the Qualcomm Stadium lot will need to be removed prior to the construction at SDSU West Campus. This is because the entire new sewer system will be installed under the roadways to ensure access for maintenance. Sizing of the sewer system will be completely based off generation of wastewater. Wastewater generation can be determined by looking at the gallons per person per day for each pad and the proposed population for that pad. Our total wastewater generation for the site is 634,500 gallons per day. Once we know the wastewater generated for a pad, we can determine the diameter of the pipe using Manning's equation. Then we must use the design criteria given to us by the City of San Diego to determine the slopes and depths of these sewer lines. Our sewer network will consist of 5,763 feet of 10-inch PVC pipe, 492 feet of 6-inch PVC pipe, and 1,246 feet of 4-inch PVC pipe, all of which will be gravity fed. We will install 26 new sewer manholes and 13 cleanouts and backflow valves for our lines. A membrane bioreactor is a definite possibility to treat our water on site. It would allow us to use the treated wastewater for irrigation of vegetation.